I want to start by thanking Myrna, obviously, for having me. It's been a wonderful visit so far. I've had the pleasure of meeting a lot of nice people. I got a chance to listen to. We talked about some very interesting research that is happening here. I even had a chance to walk on a split belt treadmill, where the left belt was going significantly faster than the right belt. It took me about half an hour to get over the limp. But I may have to go back and do the right belt faster than the left belt. It was very nice, very interesting. Also, some of the neuroimaging methods that you guys are working on with multivoxel pattern analysis, I think that's obviously something that is very much needed, as well as the treatment research that Myrna and others here are working on. I think that, unfortunately, treatment research in aphasia doesn't get quite as much attention as I think it should, which is very much reflected in the state of the art. So what I'm going to talk about today is using tDCS to treat chronic aphasia. And I think I'll just get into this. Okay, this is not... All right. Okay, I just have to push it really hard. Okay, so a little bit of background, stuff that everybody here knows, obviously, that aphasia is a language impairment typically caused by stroke in the left hemisphere. And typical aphasia treatment is behavioral treatment administered by a speech-language pathologist in a one-on-one setting. There are some more and more group settings or group treatment settings being started all over the country, these aphasia centers, which I think are very much needed. But I think that most aphasia treatment that occurs today in rehabilitation facilities is in a one-on-one setting with a speech-language pathologist. So this targets language and or functional communication, depending on who you talk to. And what I am very much interested in, among other things, is can we use transcranial direct current stimulation, or tDCS, to boost the effect of aphasia treatment? I'm going to talk about 4 studies today, and I'm going to, a couple of them have very little to do with tDCS, but I think they give nice background on sort of the thought process that we were going through when we were deciding on some of the specifics with regards to the tDCS. For instance, what part of the brain should we be stimulating, and mostly stuff related to that. So I'm going to first talk about this study called on brain changes associated with naming improvement in aphasia. Then I'm going to talk about our first tDCS study to improve naming in aphasia. And then a study 3, which is really just a follow-up to study 1, where we've added more patients and we've looked at the data more carefully. And then finally, our second tDCS study, which was naturally a follow-up to study 2, where we think we took some of the nice features of the first study and improved on some of the shortcomings that it had. So the first thing I'm going to talk about is aphasia treatment, looking at structural and functional predictors of recovery. This was a paper that came out in the Journal of Neuroscience last year. And the reason why I like to start with that is because way back when we started collecting data for this study, we were looking at where are the brain changes occurring that are associated with positive treatment outcome. And based thereon, we started thinking about, in relation to tDCS, where should we stimulate the brain? So the purpose here was to examine functional brain changes associated with aphasia treatment. Also, we wanted to look at structural damage that is a negative predictor of treatment outcome. So are there particular lesion locations that if patients have this damage, do they do particularly poorly in treatment? Treatment target here is the same as pretty much for 90% of all aphasia treatment studies: anomia, which is the impaired ability to name common objects. It's common in left hemisphere stroke. It varies greatly among patients. And it's commonly targeted in speech-language therapy of aphasia, certainly with the hope that improving things like lexical retrieval, that generalizes into discourse. Naming, of course, by itself doesn't have much ecological validity, not something that we do on an everyday basis. But of course, the assumption here is that as your naming improves, so do other aspects of your language. So in this study, there were 26 participants. They all had left hemisphere chronic stroke. It was a single event stroke, and there was a wide range of severity. So for you, they're familiar with the Western Aphasia battery, we looked at severity with the aphasia quotient, and the mean was about 60, with a large standard deviation, of course, with such a large sample of patients. There were various different aphasia types included in this study. 11 of these patients had very mild aphasia or gnomic aphasia. 10 had Broca's aphasia, 3 had conduction, 1 Wernicke's, and 1 transcortical motor. So we did not exclude patients based on aphasia severity. At that point, there was not a single globally aphasic patient that had been enrolled. Wide age range, 33 to 81. Most of these people tended to be in their 40s and 50s. Working in South Carolina, one of the things that has struck me is that 50% of all of our stroke patients are under the age of 60. So it's not very uncommon for us to have folks in their late 30s, early 40s involved in our studies. 14 of these people were women, and the time post-stroke was at least 8 months. It varied quite a bit. I mean, there were people as far out as 19 years. But what they all had in common was that they'd had a left hemisphere stroke and they had chronic aphasia. They all got aphasia treatment. So we used a treatment approach called cueing hierarchies. This is very typical lexical retrieval treatment that is administered for aphasia. I think the first time that it was described was by Craig Linebaugh back in 1977. We used 2 different approaches. One is a semantic focus and the other one is a phonological focus. And basically this goes as so. We have a corpus of pictures. We show the patient a picture. If they can't name the object or the picture, we'd give them a phonemic cue. If they can't name it after that, we give them a rhyming cue. And then the 4th level of cueing is combining the rhyming and the phonological phonemic cue. And if they still can't get it, we simply ask them to repeat the item. Once they repeat it, hopefully successfully, we go back down the cueing hierarchy. It's the same thing, very similar for the semantic focus. We just keep giving them more semantic information until the correct, hopefully, word is retrieved. If not, we go for a repetition and then go back to confrontation naming. We trained, in each one of these sessions, we trained 80 words. And they got 3 consecutive hours of treatment per day, 5 sessions per week for 2 weeks, 1 week of phonological focus and 1 week of semantic focus. Because originally we wanted to understand, is there a difference in recovery or improvement in naming, if you will, depending on what kind of treatment a given patient is getting, whether it's a semantic focus or a phonological focus. And then we wanted to look at the neurocorrelates of both of these treatments or the treatment outcomes. So the total time in treatment was 30 hours. I think this would be classified as an intensive treatment, but if you follow this literature, that's certainly what is intensive treatment to one person may not be intensive treatment to another. I've seen something called intensive treatment where they got 3 hours of treatment 2 days in a row and called it quits. I'm not so sure that most of us would call that intensive treatment, but that was our definition. I said that 80 pictures were targeted with each one of the cueing hierarchies. All right, so we have now completed 30 participants, but I'm only talking about 26. And at that point, we had scanned 26 participants 6 times, twice at the beginning, twice between the semantic focus and the phonological focus, or depending on what order of treatment you got, and then twice at the end. And those different treatment sessions were always done 1 day apart. So let's say that a patient started on a Thursday, they would get scanned Thursday and Friday. The following week, they would get treatment. Week after that, actually, I think I show a schema of this on the next slide that I think explains this a little bit better. Anyway, a lot of MRI. The treatment outcome was naming common objects during the fMRI scanning because we wanted to relate their naming ability to how well, to their brain activation. The naming attempts were recorded with a non-ferrous microphone. We recorded that, and then there was a speech pathologist that scored these naming attempts offline. So we knew at what point in time was this person able to name an item correctly, what time, when did they make a phonemic paraphasia, semantic paraphasia, etc. So here's basically the paradigm that every one of our participants went through. They started with the 2 fMRI sessions at the beginning, as well as structural MRI. We did 64-direction DTI, T1 and T2 MRI, ASL perfusion, and FLAIR. Then they had 1 week of treatment, 1 week of rest. At the end of the rest week, they had 2 more fMRI sessions, another week of treatment, and then at the end, 2 more fMRI sessions at the end. Okay. So to make a long story short, here is the treatment outcome. So these are change scores in correct naming. So remember that we were trained, this is for trained items. So this is the range of responses from the worst response or the poorest response at number 1 to the best response in number 26. So for these 2 treatment approaches, some of the folks, certainly their naming seemed to improve a lot, but for at least half of them, if not more, probably more than that, they really did not show a good response at all. So not uncommon in aphasia. Some people do really well and some people don't. Why is that? And that's one of the things that we're interested in. So if you look at brain damage that is associated with poor outcome, what we found was doing lesion symptom mapping using Chris Roden's NPM software. We found that there was this posterior locus of lesions there, that if patients had damage to this area, they tended to do fairly poorly, and that's what you see in the red column there. On the gray one, however, shows the patients that had that area spared, and those did considerably better with the naming treatment. With regards to the functional MRI results, this is looking at change in activation comparing the first 2 sessions to the last 2 sessions as a predictor of outcome. So we wanted to understand what are the areas that, when those areas change in activation comparing pre to post, that predict positive or negative treatment outcome. And what we found is that what you see there in red, the red clusters, those are the areas that had a positive correlation with treatment outcomes. So patients that showed a lot of increase in those areas also tended to do relatively well in treatment. The lesion overlay map is what you see there with multicolors. Okay, the reason why I think this is important for the tDCS study that I'm going to talk about next, and I think I get into this here, because we thought, at least based on those results that we had in those 26 participants so far, using this univariate approach, which I think was a reasonable way to look at this in the beginning, that the left hemisphere change in activation supported improved naming. So going way back when we first did our original tDCS study, these clusters that you see, actually, at the beginning when we analyzed about 20 subjects, or maybe less, maybe 18, we really just had the anterior cluster there. And we thought that this change in activation in the left frontal lobe is really what is driving treatment outcome. So that was something that we thought was important for where we should stimulate. So that gets me into our first transcranial direct current stimulation study to treat aphasia.
Julius, would you like questions at the end, or do you want to?
Either one. Sure. No. Let's get them now.
So can you go back to, so a lot of these people will have strokes right where that.
Yes.
So
yes.
How did you co-register these brains, and what was, are you going to tell us a bit more about the details?
No, I was not.
So
we use lesion masking to co-register them, but here's the trick. So either if you have a lesion in that area, you can't have any change in activation, right? So it could be 2 things happening. Either that you have a lesion there, or if you have an intact, if the cortex is intact, it did not increase in activation that was commensurate to the change in your naming score.
And so these are significant, and if so,
yes.
what kind of measure did you use for significance?
We used the standard FSL threshold of z-scores equal to 2.3, corrected for multiple comparisons.
How? What correction?
You know what?
It doesn't matter. I mean, that's too picky.
FSL uses a weird correction that is never easy for me to explain. SPM certainly is easier, but
okay. Yeah, that's fine.
But it's what they call robust. So, okay, so I started getting into this mainly because of Mark George, who is at the Medical University of South Carolina. He's been doing brain stimulation research for years, mainly treating things like depression. He had I think that he was very instrumental in getting TMS approved for treatment of depression and has been doing brain stimulation studies for years, starting back in the NIH, I think in the early 90s. And I've been talking to him about the lack of response to aphasia treatment and whether there was anything that we could do to actually improve our treatment outcomes. And he was the editor and is the editor of Brain Stimulation and suggested that we look at this new technique called tDCS. Because I wasn't very fond of TMS. Anybody here do TMS research? Yeah,
No offense, Dave.
So we wanted something that was a little bit friendlier on the scalp. So I thought that tDCS, at least what I had seen so far from Paulus and Nietzsche in Germany, it seemed to be promising. And it seemed to be something that I thought was worthwhile to look at. Because patients with chronic aphasia, let's face it, I mean, when it's in the chronic phase, many of them do not show any improvement. So I think that we were really looking for something that we thought might boost our effect. And that's how we got into this. tDCS, for those of you who are not familiar with this, it induces a weak electrical current, usually 1 to 2 milliamperes between two electrodes, an anode, which has a positive charge, and a cathode, which has a negative charge, placed on the scalp. What we have there is just a very simple picture showing the setup that we used in our studies. This is Frank, who used to be a postdoc in my lab, showing the anode electrode being placed on his left frontal scalp, and we had the cathode electrode on his right shoulder. So anodal stimulation is thought to have an excitatory effect on the cortex, and cathode stimulation is thought to have an inhibitory effect. So there's been an explosion in this kind of research. I mean, there's more and more studies being published on this all the time, showing some very positive results, I think. At least for us at the time, it seemed logical to try this in aphasia. I'll maybe touch on the BDNF stuff at the end if I get a chance, but there are a lot of different people trying this. This one from Gottfried Schlaug, looking at motor recovery, and there are many others. We wanted to understand if we couple tDCS with aphasia therapy, does it actually enhance the outcome of the treatment? And for this initial study, there were 10 participants. They all had chronic aphasia following a left hemisphere stroke. And we had various aphasia types and severities. I don't know about you guys, but our pool of aphasic folks, getting somebody to participate in this right off the bat, we basically took all comers. We wanted to understand, is there any hint of an effect? And if there is one, we would take this somewhere further, which is basically what we've done. So all of these participants had treatment, which we called visual speech perception to treat anomia task. This was published in the journal Stroke. This is a really simple approach. All you have is, you see a picture on a computer screen, and then immediately following it, you hear a word, and you also see the speaker's face on the monitor, and either the word that is spoken does or does not match the picture. It's a very simple task. They have two buttons that they press: green for correct match, red for incorrect match, and what the computer program does is that it gives them immediate feedback. And it was really just from a study where we were looking at the effect of visual speech perception on treatment outcome. And we found some nice findings in that study, but that's the treatment task that we used. There were 2 weeks of treatment, 5 sessions per week, and it was very short. It was only 20 minutes because at that point, people really were not doing tDCS beyond 20 minutes. Now, maybe up to 30 minutes, but I haven't seen very many people that have gone beyond that. Yep.
What was the duration of treatment using your visual speech perception task in your 2009 paper? Presumably it's longer than 20 minutes.
Yes. So it varied. I think we were actually back then, we had like a accuracy threshold. it was anywhere between 15 to, I think, 35 minutes. So it varied among those participants. Yes. For this one, we like to use it because just to keep this very controlled, so we could compare the sham and the anodal conditions. This was a double-blinded crossover study. There was 1 week of anodal stimulation and 1 week of placebo, which was sham. Let me explain the sham. For the anodal stimulation, the stimulator was turned on for 1 milliamp for the whole 20 minutes of the treatment. To accomplish the sham, we would turn on the stimulator, ramp it up very slowly for about 30 seconds, and then turn it off during the next 30 seconds. And the reason why you have to do that is because when the stimulator comes on, you feel very definite tingling on the scalp. And some people actually think that it itches a little bit. It's controversial whether this is a good sham or not, but it seems to be what everybody is using. We are certainly looking at some other options, which I can talk about at the end if anybody is interested. The electrode placement, I touched on this briefly earlier. The anode electrode was placed on the left frontal lobe or the left frontal scalp, and was really based on those fMRI results that we had with about 18 to 20 subjects in the previous study. The cathode electrode was placed on the right shoulder. And this, when I say that it was targeted with fMRI, what we tried to do was to make sure that we were not placing the electrode or the sponge directly over the lesion. So everybody had structural MRI and functional MRI, where we looked at brain areas that were active during naming. Now, whether that's an overkill, I guess is up for a debate because the sponges are very large. But we thought that this was probably the best way to start out with it. The outcome measure was naming, even though this is not a naming treatment. It really isn't. It's just picture word matching. We looked at both trained items and generalization. So there was a corpus of words that were trained as well as control words, and we looked at how if they improved their naming on both types of items. So here are the results from the trained items. This is the whole number of items that was increased. So this is change score there on the y-axis. The whole number of words that increased for the whole group comparing anodal to sham. This was statistically significant at the 0.04 level, but to us there seemed to be something going on there, that people tended to do better following the 1 week of anodal compared to the 1 week of sham. Also with untrained words, we had a larger corpus of untrained words. It was twice what we had for trained words. So if it seems like generalization actually was much better than the actual trained items, that was not the case. It was simply that we had a greater number of words that we used as the untrained corpus. This was not statistically significant, even though it looks like it should be, but there was a lot of variability within the subjects, and I'll get into that in a little bit. Okay, so at least following this, we thought, well, maybe there's something here worth pursuing. That anodal tDCS stimulation of the left frontal lobe improves naming in some patients. Okay? Because treatment response varied widely among the participants. For 5 of them, there seemed to be a far better response with the anodal tDCS compared to the sham condition. For 4, it was pretty much equal, and 1 person really did not improve at all with either one of the conditions. So when you collapse across these subjects, yeah, it was statistically significant for the trained items, but a lot of variability. Okay? Uh-huh.
Just, do we know that TDS by itself doesn't improve naming, i.e. that it's boosting treatment versus just boosting naming?
Yes. Oh, I see what you mean. I don't think anybody's looked at that. I thought you meant that can it boost the naming effect without the actual behavioral treatment. That has been looked at. But whether it boosts...
In other words, whether having the electrode on simply gives you better access to your lexicon.
Yes, there's a recent study that came out, and I became aware of this about a couple of weeks ago, where they did cathodal stimulation, which is thought to be inhibitory, on the homologue of Broca's area in the right hemisphere. Perhaps that was in any of your stuff, no?
No.
That's Leo Cohen, right? Leo Cohen and some other people. Yeah. Yeah. And they seem to have an effect without any treatment. With simply by using this inhibitory stimulation, if you will, they seem to get an improvement in naming.
And there was a study in Alzheimer's patients without associated treatment. So there's been several studies without concurrent treatment that show benefit.
Yes. Okay. So as we kept doing this, the original treatment study that I talked about in the beginning, this was supported by an R1 grant. We've been collecting data on this for about 4 years now. When we looked at the response of these participants right here, it seemed to be the case that the people who really had a good response seemed to be getting their stimulation in the vicinity of the lesion, so close to the lesion. And what we thought was that perhaps what is happening here is that it's the peri-lesional areas, at least what I call peri-lesional areas, the area surrounding the damage, where those favorable brain changes were occurring that were associated with the tDCS. So we went back and we looked at the previous data that we had from our subjects getting the treatment without tDCS, those 26 subjects that we have scanned before, were treated before, and we had added 4 more. This was just a follow-up then, and we wanted to understand, is treatment response really associated with peri-lesional brain changes? And by now we have 30 subjects that have gone through the 30 hours of treatment and gotten the 6 fMRI sessions. It's just a lesion overlay map from these patients. Just showing that in the areas that are red, at least 10 patients had damage that was in each one of those voxels. Okay, so we wanted to look at those peri-lesional regions. Well, how do you define what is peri-lesional region? What is peri-lesional to me may not be to somebody else. So we really didn't have a good way to define this. So what we did was that we looked in increments of 3 millimeters at areas going away from the lesion at both perfusion using ASL as well as MD values with DTI images. And we wanted to understand, is there something about the physiology? So we didn't have a very good way to define this. So we thought we're going to look at physiology. So we're going to look at both perfusion and MD values and increments going away from the lesion, and perhaps that is going to give us some idea of what we should call this peri-lesional region. So for both using ASL, this was, I think, in 21 subjects, we looked at the increase in cerebral blood flow going directly surrounding the lesion. We actually did not look at the first 3 millimeters because of partial volume. But beyond that, if you look at the amount of perfusion using CBF values, and I must say that the actual picture that you see on the left of the brain, it's a little bit misleading because we were not looking in white matter. It should only actually be in the gray matter part of the image. Anyway, we looked at what point do we see differences or non-significant differences in these values going away from the lesion. And interestingly enough, what we found was that between the 12 and the 15 to 18 was when we did not have a statistically significant effect anymore. It seems like an arbitrary method, but for us, it seemed to be the most principled way that we could come up with something called a peri-lesional region. We also correlated those two and found out that there was a fairly high correlation between the two. So what we were looking at here with in these peri-lesional regions was really the area immediately surrounding the damage out to about 15 millimeters. You can see this in a single subject here. I filled in the lesion there in red, and then the peri-lesional regions in the frontal lobe, in the temporal lobe, and the parietal lobe are then shown in different colors. We wanted to not only see whether change in activation in those peri-lesional regions was associated with outcome, but if it was, where specifically was that? Was that in the frontal lobe, the parietal, or the temporal? We did that for all the subjects, and what we found was that if you look at change in activation only in those peri-lesional regions before and after, that there is a significant relationship between that change in the left frontal lobe for the whole group, so that the greater the increase in activation in that frontal peri-lesional region, the better they did in the naming treatment. And just for fun, I put up there the breakdown based on what aphasia type they had. Okay?
So the y-axis is percent?
It's a change in z-scores. Yes. And then changing correct at the bottom there. I must say, though, that this is a little bit misleading because if you look at the change in activation in the left frontal lobe, it certainly correlates fairly well with change in activation in the temporal and the parietal lobes. So these are redundant factors. Okay? So what are the implications for this? Well, we think that more specific than the first study that I showed you with the 26 participants, that at least for those folks that we have looked at so far, that those people who do well in treatment, that activation increases primarily in the regions that are immediately surrounding the damage. And we had these results a while ago. We haven't written them up for publication, but we thought that for the follow-up tDCS study, which is the last study that I'm going to talk about today, instead of just focusing on the left frontal lobe, that we would try to target the peri-lesional regions that show significant brain activation during naming. And in this study, we also wanted to be a little bit more specific with regards to who was included. There were 8 patients, all with chronic aphasia. 7 of them had anomic aphasia and 1 had conduction. And all of them had primarily posterior damage. Not a single one of them had frontal lobe damage. So this was primarily in the parietal or temporal lobes. We used our picture word matching task as the treatment as before. And the tDCS, very much similar to the previous study, we compared 5 sessions of anodal tDCS to 5 sessions of sham tDCS. And again, the electrode placement was fMRI guided, where we tried to at least put the pads over regions that we thought at baseline were activated for picture naming. The treatment type was blinded to the participants, to the clinician administering the treatment, and the clinicians who were scoring the outcome tests. And Chris Rorden, who is my main collaborator, been my main collaborator for years, he made a really nice hardware plus software where the clinician simply entered a participant number into the computer, and then the computer actually started the stimulator. And so the clinician did not know whether this person was getting at any given time the real tDCS or the real anodal tDCS or the sham. Also, we videotaped all the naming sessions before and after, and the clinicians who scored the outcome tests were blinded to what kind of treatment they were getting before any one of the outcomes. And the participants, of course, we tried to have them blinded as possible with the tDCS sham setup. One of the problems with this was that these patients had fairly small posterior lesions, so their naming already was fairly good. So we wanted to focus here on reaction time for naming rather than accuracy, because we thought that it would be a more sensitive measure of outcome rather than accuracy by itself. We used a voice response key with E prime. It worked really well. We only scored correct naming attempts for reaction time before and after. And what we found was that testing those patients immediately after treatment, there was a significant decrease in reaction time following the anodal tDCS compared to the sham. So I guess I can't walk up there. I guess I can do it right here. So here we see the decrease in, so here's baseline, and here's the decrease in reaction time for the anodal, and here's the decrease in the reaction time that you can then, I guess, contribute to the task, the naming, the picture word matching task itself. We also tested them at 3 weeks post The treatment effects seem to be there still for the anodal tDCS, but a lot more variability for the sham, and that was also statistically significant. So, okay. So what does that mean? It seems to be the case that anodal tDCS enhances the effect of behavioral aphasia treatment. I want to emphasize that these treatment effects are very small. For many different reasons. I think this is very difficult to do. My lab, pretty much when we run these studies, we shut down pretty much everything else for about 2 to 3 months. The logistics are very difficult. So I think to do this on a larger scale, I would prefer to have more treatment sessions. But at least I think that now we can say that perhaps there is something there that is worthwhile looking for even further. We certainly need to verify that this is the case. We don't know very much about dosage. We pretty much know nothing about dosage. How long should you stimulate? How long should that be before or after the actual behavioral treatment occurs? We can go to some of the behavioral stuff from normals to try to guess on some of these things. But I think there's a lot of work left to be done. Dr. White earlier asked about stimulating without the treatment. Well, should we be doing anodal in the left hemisphere and cathodal in the right? Because there seems to be very significant evidence that suggests that decreasing activation in the right hemisphere promotes better outcome in aphasic patients. But then again, I saw a study, I think on Monday in stroke, where they did anodal stimulation of the right parietal lobe, and lo and behold, they got a positive effect. So I think that there's a lot left to be done here. Another thing that it seems to be really popular these days is looking at BDNF, or brain-derived neurotrophic factor. This is from Paulus's group in Germany, where they looked at motor evoked potentials. That's what you see, the amplitudes there on the y-axis. In normal participants, and they looked at it comparing people who had this BDNF, brain-derived neurotrophic factor polymorphism. They had if the response to tDCS was different to those participants who had BDNF polymorphisms as opposed to those who didn't. And what they seemed to show there was actually the opposite for tDCS as compared to theta burst, TMS. If you look at their paper, this came out in Brain Stimulation last year. And this was shown off for anodal tDCS, both with anodal tDCS as well as cathodal tDCS. For the cathodal, the effect seems to wear off about an hour into after the stimulation. So they're really just charting their motor evoked potential after tDCS is over. So I think that this is something that needs to be taken into account perhaps in future studies, but I don't know. It seems a little bit like mirror neurons to me. Everybody talks about it for a while and perhaps it'll fade away. The other thing that may be very important, this is stuff that we worked on with Marone Bixham at City College of New York, and that is using finite element models looking at tissue density as a predictor of where your current is spreading. We published a case study in brain stimulation with one of our patients where we tried to show where the current was flowing in one of the previous subjects that actually had responded well to treatment. And just to humor me, Marone actually made this picture that shows that using a setup with very small electrodes, so 4 cathodal on the outside, so what we see right here, these 4 cathodal electrodes right here, and 2 anodal electrodes in the middle, it should be possible to get very focal stimulation of the peri-lesional cortex. Now, we don't know whether these models actually correspond to the effect of the treatment itself. I mean, it seems to show the current distribution. But then again, we don't know whether there's a one-to-one relationship between the intensity that you see in these scales right here and the actual amount of stimulation that, or the amount of response that you're getting from the cortex. So maybe very important for the future, we'll see. But I thought that was interesting. So Okay, I think I've gone over my time a little bit, but I wanted to acknowledge my collaborators, my postdocs, Jessica, Paul, Dana, and Julie, my graduate students, and certainly my collaborators. Oh, I forgot to change that. Chris Worden used to be at Georgia Tech. Originally, he was in South Carolina, but we just lured him back to South Carolina. Leo Bonilla and Marone Bixon. And, of course, my grants from the NIDCD. Thank you.